Okay. Let's make a start, shall we? Good morning, everyone, and welcome to our inaugural Day of DH here at the University Library at the Chinese University of Hong Kong. As many of you will know, this is the final event in our Digital Humanities Initiative that has been running since September last year and will, thanks to generous funding and contributions from Dean Tang and Professor Yellen will be continuing next year as well. Today we've got an exciting program in store for you. First, we obviously have our keynote address from Dr. Donald Sturgeon. More about this in a moment. This will be followed at 11:30 by a tour of the DH lab and an exhibition in the makerspace of our new 3D printing capabilities, which will be making an appearance, I hope, in history department courses from the year after next with our 3D printed museum course that I'm proposing. So that's at 11:30. We will then have lunch, about which time we should get an influx of people from HKU in the form of Professor Javier Cha and his students. At 2:15, I will be briefly introducing some of the DH opportunities here at CUHK. And leading some interesting activities where you'll be collaborating with the students from HKU. Just in case you don't know, these students are from their new humanities and what's it called? Humanities, BA in Humanities and Digital Technologies is the name of the program, which started this year under Professor Cha and Dr. Anya Adair. In the law school. You'll get to meet them and collaborate with them. And then at around 3:15, the students from HKU will be presenting some of their projects in the hope of getting feedback from you on their ongoing work. So that should be very, very interesting. Anyway, let's move on to our first event of the day. So it's my pleasure to introduce our keynote speaker, Dr. Donald Sturgeon, Assistant Professor of Computer Science and a member of the Institute of Medieval and Early Modern Studies at the University of Durham. Trained in the UK and in Hong Kong from 2015 to 2019. He was a postdoctoral fellow and then college fellow at the Fairbanks Center and what I think has now changed names, but the East Asian Languages and Civilizations Department. I don't know if East Asia still has a civilization or not. Who knows? Anyway, the East Asian Studies Department at Harvard. Dr. Sturgeon is a digital humanist and a sinologist with a deep commitment to using technology to better understand pre-modern sinographic philosophy and literature. Many of you in the room will have used his groundbreaking Chinese text project, which is a major online collaborative digital library for pre-modern Chinese texts. I know I make constant reference to it. He's also the author of numerous path-breaking articles in digital sinology. I particularly commend to you his 2018 Digital Approaches to Text Reuse in the Early Chinese Corpus, which appeared in the Journal of Chinese Literature and Culture. He's also made important contributions to the development of classical Chinese OCR, an area, of course, of great interest to us at CUHK, and the use of linked open data and crowdsourcing the historical record. Today, however, he will be speaking to us on the topic of working with pre-modern Chinese texts in the digital age. Dr. Sturgeon, Donald, the floor is yours.
Thank you very much. Thank you very much, everyone, for coming, and thank you very much. Thank you very much, Professor McManus, for that very kind introduction. It's a pleasure and an honor to be here starting off today's exciting session, and I'm really looking forward to hearing from students from HKU later on and discussion and feedback from all of you. So I'm going to try and keep this fairly short. As has just been mentioned, a lot of the things that I do have connections to something called the Chinese Text Project, partly because we had a workshop on that last week here at CUHK, which again I was delighted to be involved in. I'm not really going to focus on that a lot today, but you can probably, if you look carefully, you'll see that a lot of the examples that I'm using are connected with that in some way. So what I do want to do today is to focus a little bit more, rather than on specific applications or specific databases, on more general questions about organizing textual data and how we work with textual data in projects like CTEX, but also in other projects and just generally. So I'm going to focus on this idea of representations and how we represent textual content. And I'm going to start by making a few comments about pre-digital organization of textual data. Then I'm going to move on to what you can think of as being the sort of current digital baseline, or the digital baseline that we're really familiar with over the last few decades, really, from dealing with texts in computational contexts. Then I'm going to move on to some slightly newer things, how we connect text and data digitally, and how we connect data and data at a global scale. So this is really connecting to this idea that was just mentioned of linked open data and something called the resource description framework. So how we can go beyond having individual small projects that have their own data, that have their own curated materials, and how we can connect these seriously at scale so that we can ask more sophisticated questions of larger bodies of material through digital querying. And general motivation for today's talk is that different representations of what, in some sense, is the same information or the same content are going to make answering some kinds of questions easier than other representations. So it matters how we represent our content, essentially. Okay, so I'm going to say a couple of things about pre-digital organization of textual data. I should say this is an enormous topic, and I'm not an expert on this topic, so I really just want to mention this as a kind of piece of background. One of the kind of most obvious examples of this in the Chinese context is probably the development of leishu, which are often translated as Chinese encyclopedias in English. That's maybe not a very adequate translation because that's somewhat misleading in terms of the actual contents of these materials. But what these do, or what many of these do, essentially, is to organize textual material from classic texts, so from widely used prior texts like the Book of Changes or the Shangshu or the Confucian Analects, say, and organize these materials according to different principles. So of course we have these texts of the Analects, you have the first chapter, the second chapter, the third chapter, the whole thing in a long stream of writing. But another way of organizing that is to organize it thematically and to connect it with similarly thematic groupings of citations from a body of classical materials. And this is the kind of thing that many leishu do, such as this example on the right from the Yiwen leishu. Materials are organized according to some kind of classification, generally hierarchical. So in this case, we have this tianbu is the kind of large organization of things connected to nature or naturalistic concepts. Then this is subdivided into things like tian, ru, yue, xing, etc. And within each of these headings, we then have these citations organized according to this particular set of organizing principles. And this is a kind of transformative way of organizing this primary source material. It makes it possible to very quickly locate information according to this conceptualization of knowledge, according to this hierarchy of how the information is organized. If you want to find all of the important citations from these classic texts that relate to say, the moon or the sun, you just need to go to the correct heading according to this conceptualization, and then all of the citations are organized for you there in this convenient way. So I'm not going to say much more about that here, but I want to use that to motivate something which is a little bit more directly related to digital indexing of texts, which is the development of modern indices and concordances for Chinese materials. And this is primarily, I would say, an early 20th century development for Chinese materials. We have things like the Shuoyuan Inde. This is one of a series of indices created by the Harvard Yenjing Institute in the early 20th century. And this is doing something somewhat similar to leishu in that it's providing an index of the general kind that we're familiar with from modern printed texts, where at the end of your text you have an index that tells you certain things about where to locate concepts within the work. And how these work is by having a head word, like these two we've highlighted in purple here, in these cases referring to particular historical individuals. And alongside these, we have short editorial summaries of some particular anecdote in this case that occurs in this early text, describing what the anecdote is. And then importantly, we have a reference which tells us precisely where in this potentially long work we'd find this particular anecdote. And so this includes some kind of referencing system that allows us to locate precisely in this longer work where this piece of information comes from. So this is one type of index that we have. One thing that I want to highlight here is that the way these indices were created in the early 20th century, typically different senses of the same word would be disambiguated. So you might have, in this case, we have two head words, shin here, which mean different things. So in one of these, this is shin in the sense of heart or heart-mind. And the second one here is shin in the sense of a constellation. So Chinese categorization of constellation, this is a separate meaning of shin. And these are disambiguated here as having completely different head words, allowing you to locate the cases in this particular text which are related to one of these two senses quite separately. So at the time, these were really revolutionary resources to have access to for the same reason that Leishu are. They give you another way of locating material without having to say, I want to physically read through this entire work page by page to locate what I'm looking for. A second kind of index called a concordance is something which is probably even more familiar to us now from the way we interact with texts in the digital realm. And this is based on a very, very similar kind of idea. Again, we have head words, like this one here, 学. But this time, instead of indexing things according to kind of interpretation of the editor or the indexer, it's indexed according to a much simpler mechanism, which is to say, I'm just going to go through this entire work, and I'm going to exhaustively write down every single instance where this particular word appears. And that's what these circles are doing. The circles are essentially just a kind of wild card saying, this is where this word that I had here appears. So we have 十岁有学. It appears in some particular location in this text. Again, we have this indexing idea. So this tells us which page of the published work we'd find this instance on and which line. And so we can use this to locate the textual references very, very quickly. So you can think of this as being a kind of precursor to full-text search. This is very similar, or appears very similar to how full-text search works in modern digital library systems. This will locate all of the instances of a particular term for you. And so if you do the same thing, if we look in the same text for exactly the same word, we find something very, very similar if we do full-text search. One reason for mentioning this example is that we don't actually find exactly the same thing if we do this. If you look carefully at what's going on here, this is again slightly different because the indexing here has been done manually by humans in the concordance here. And so it's indexed by words rather than characters. And again, depending on the index, you may have this semantic disambiguation where you have multiple head words which are the same literal characters, but referring to different concepts. So this is slightly different to how digital indexing typically works in full-text search systems. There's some pretty good reasons why we don't use these so much today. One of the reasons that these things are unwieldy is that if you have long texts, these indexes are going to be very large. And somebody has to create these. If we want this semantic content to be indexed, at least in a pre-digital context, somebody has to go in and decide, is this particular instance of shin, is this referring to heart, or is this referring to a constellation? So they're expensive to create, and they take up a lot of space. A second thing I want to highlight about these that's maybe less obvious is the way they're created, or the way at least some of them were created. This is an example from Indexing Chinese Books, published in 1930 by the editor of the Harvard Concordance series, corresponding this particular example, again, to the index to the Shoyuan. And what this is demonstrating is the way these actual concordances had to be produced in the first instance. So in the first instance, if you want to create a concordance, you have to first of all have some copy of the text you want to index, because that's how you're going to get your page citations, line numbers, and so on. But you also have to exhaustively go through this and identify the things that you're interested in. And the way this was done practically in the 1930s was to go through and physically annotate instances of things that were the kind of things that we wanted to index in the text. And I've highlighted just one of these here in this annotated page. This is an example where we have 孔子曰子也非汝所己也. We have this citation here. And the 词, this particular character, has been highlighted with an annotation that says, well, this 词, it's something special. It refers to a person, and it refers to a particular person. It refers to Zigong, who is one of Confucius's followers. And so this information is annotated here, and the reason it's annotated is so that it can be indexed later on, so that this can be added, this citation to this page can be added to the index in the appropriate place. And this is something that we'll come back to later on in the talk, because something very similar has a lot of obvious applications in digital libraries and in adding semantic information on top of digital texts in a very similar way to achieve some similar aims to those that were achieved with concordances, and to perhaps bring back some of the things that we've lost in going from concordances and indexes into full-text string-based search. Next thing I want to highlight is something you're probably familiar with, which is that we have a ton of digitized Chinese pre-modern material. There are enormous collections of this. If you think about things like the Sikuquan Shu, which was digitized many years ago, that's something of about 2 million pages or longer, substantial body of material. But now we have hundreds of times more material than that, digitized in the sense of having been scanned by commercial companies or by university libraries or by large-scale scanning projects. There's a huge amount of this material, and this is obviously extremely useful for all sorts of purposes. If you want to look up material in a particular edition, if you can do it from the comfort of your home through your web browser, that's going to save a lot of time versus going to a university library, particularly if it's a university library somewhere on the other side of the world. And part of the reason we have this is because this process relies on mechanical processes like scanning. So there's a lot of detail required in scholarly digitization of these manuscripts. I don't want to kind of trivialize this, but there's a sense in which in the current era, creating digital surrogates, digital images of physical materials is a mechanical process. You can take out your phone, you can take a photograph of this slide, and you'll have a copy of that. It may not be a perfect digitization of it, it may not be a perfect surrogate, but creating these things is a mechanical process that can be done relatively cheaply. So we have tons of these images, and we have OCR, which I imagine most of you are familiar with, and you're probably also familiar with the idea that OCR introduces errors, particularly for pre-modern materials. They may not be clear scans, the documents themselves may have unclear parts of them. There are all sorts of reasons why we might have errors due to OCR digitization. And obviously at the other end of the scale, another way of creating these digitized transcriptions of material is through scholarly digitization, where we have manual editing, annotation by experts. The nice thing about this is that we have this promise of perfect results without these errors, but the flip side is this doesn't easily scale to enormous amounts of material in the same way that automated processes such as OCR can very easily do. So hopefully a lot of you are familiar with the question of why OCR might be difficult, but also why it might be a useful thing to do. And this is coming to the first of these different representations of text that I want to talk about. So you have these two very different digital representations of text. So in a sense, the same kind of objects that we want to create digital surrogates of, we can have digital surrogates in the sense of images, which in some sense contain nearly everything. Most of the questions you would be able to answer about a physical object, you'd be able to answer by looking at a sequence of images of the page. Perhaps not every question, but most questions. But these are hard to navigate and process. If you open these up on your computer, you can flip between pages, but that's kind of about it. And the second representation, of course, is a transcription, where what I want to emphasize here is what's really been added is additional semantic content. So something has been added about the meaning of the symbols and the dots on this page. To a computer, an image is just a sequence of dots. It's just a bunch of dots. It doesn't really mean anything. All it means to a computer is there's some different colors here, there's some brown and there's some black in different places. When we turn this into a transcription, a digital transcription, we're adding information that tells us something about the meaning of the content here. And so I've chosen two images they're actually from the same page at the bottom here. These are both from the same page of the same manuscript. And I would assume for those of you who are Chinese speakers, if you look at these two characters, you're going to tell me they're the same, right? They're the same character. They're obviously, to a human being, the same character. They appear similar to us. Are they identical? They're not identical. They're not identical in a number of different senses. They're not identical in that trivially the dots are not all exactly the same dots and exactly the same colors, but there are also significant differences between these two. There are slight differences in how the strokes have been made here and the spacing between them. And this is really why OCR is challenging to a computer, or one of the reasons why it's challenging, is that we think of these things as being the same, but they're not literally the same. They're not even close to being literally the same. And the digital representation that a computer has access to is simply this sequence of different colored dots. And so it's a challenging task, of course, to go from these different colored dots to say these things are really the same. And so this is what OCR essentially tries to do. It tries to turn our representation as image into a sequence of characters where each character is internally represented by a number. And this is why once we have this representation, it becomes trivial for a computer to answer all sorts of different questions about the text because it's simply recorded as a sequence of numbers. And so instead of saying, well, this image here has a whole bunch of dots and this one has a whole bunch of different dots, now this is much simpler because this D here is exactly the same number as the other ones here. And so it becomes trivial to ask questions about content on the level of sequences of characters. So I would say that this has been one of the #1 transformative applications of digital libraries, having access to full-text search, and it's basically made possible by this representation. So we're going to represent characters as being the kind of individuated things that are the same or different in our sequences. And so obviously these make possible all the things you're familiar with from digital libraries. You can search for references to text in huge corpora almost instantaneously. And the key thing here is it's a mechanical process. This isn't something where you go to your university library and you fill out a form and ask them to go and return this information for you. This is something you do in your computer, and within a fraction of a second, you have all the answers. And there are obvious extensions of this to things like text mining. There are extensions to summarization of large bodies of text. So as soon as you can do this kind of simple mechanical search, you can say, well, where do these strings occur across a large body of material? So if you're familiar with things like Google Ngrams, this is exactly the same kind of idea here. What we're plotting is the proportion of all texts written at a particular year in time, which contain a particular sequence of characters. These are the kind of trivial questions that a computer can answer, and can answer at really large scales, and this idea of scale then makes it possible to interact with these texts in ways that really go way beyond the kind of things you could do with concordances. And if you were at the workshop last week, you will see examples like this, where we use exactly the same idea to say, well, a computer can easily look for sequences of characters and say, do these same sequences appear in particular places? Do we have this kind of reuse where material is copied in unattributed form across different works? This becomes very, very easy to identify. So this is a simple example of text mining that becomes possible as soon as we have this new kind of representation. And again, we can have different ways of visualizing and summarizing this, because we can now extract using computational methods very, very quickly millions and millions of these kind of small similarities that individually are meaningful. And we can ask a computer to try and summarize these in some way that makes sense of an amount of material that wouldn't really be interesting or feasible for us to read through each individual pair of similarities. So this is a summarization here of all of the similarities of this kind across all of the texts in the classical corpus and the pre-Shinhan corpus, indicating which pairs of texts have larger proportionate reuse of this kind between one another. And there are many other kinds of text mining that you can do based on the same kind of approach. A lot of these are fundamentally based on the same kind of idea as full-text search. So looking for strings of characters that occur in different places. So for example, looking at different patterns of grammatical particle usage here, the ye's versus the e's. It's easy to search for these, but also then becomes possible to summarize this information, because we can look not just at individual instances, but look at how many times these instances occur within particular bodies of text. So what this visualization here is showing is patterns of these two grammatical particle usages in chapters of one text as compared with chapters of another text. So again, summarization, but based on this very, very simple idea, comparing things that we now have easy access to in this representation of our text. This is a slightly more complex version of exactly the same thing, where now we're actually looking at a bunch of different grammatical particles, and again, this is an example similar to ones we looked at in the workshop last week, where essentially what we're doing is creating a visualization of how particles, grammatical particles, are used across three separate texts. And this makes it possible to do exploratory text mining to say, well, where are there patterns here? Patterns of not just one particle or two particles, but of all the grammatical particles that we know occur in these texts. Are these used in different ways across these different materials? Summarize this information for me. Summarizing the information is something a computer can trivially do when it has this representation. Of course, interpreting this information, interpreting this output and telling us whether this tells us anything interesting about our text or not, this is something which is left up to a human as an interpreter to say, can we see interesting or meaningful patterns on the basis of this, and can we explain what they are? A computer can tell us literally what they are, whether, for example, there are fewer of all particles in some group, or whether there are more of one particle or two particles in some subset of these chapters. Whether or not that's interesting or meaningful is something which somebody who has understanding of the content of the text and potentially their textual history is going to have to be involved in the process of answering. Okay, so we have these two representations. How do we get between the two? I'm not going to talk a lot about OCR, but I want to highlight a couple of features of how OCR generally works that I think are going to be important when it comes to more sophisticated representations of text rather than just plain text that we're familiar with as transcriptions. Probably the most important point here is that optical character recognition generally is going to rely on supervised machine learning. So this could be deep learning, it could be traditional machine learning, but it's going to rely on supervised learning. So what does that mean? Well, if this is our input, we have this image, and we want to create a transcription of it, there are several things we can do here that just use simple rule-based approaches. So by rule-based approaches, I mean the kind of things you could write a Python program to do by saying, look at this image and look at some of its properties and split it up in various ways. One thing we could do would be to split it up into individual columns. There are some quite simple algorithms that we can do to do that reasonably successfully. And we can also do the same thing vertically to split these up into individual characters. There's some complications, but these are the kinds of things that we could do using rule-based processing of images. The challenging part isn't so much that. The challenging part is given each of these things, each of these sequences of pixels or dots that looks like a character, to decide which character is it. So given this image here, which character of all of the tens of thousands or hundreds of thousands of possible characters is this particular one? And this is a task where we really need to use things like machine learning, because you don't want to be writing a Python program that has some kind of case-by-case processing that has a different set of instructions for every one of these 10,000 different characters. That's an almost impossible and extremely thankless task to get involved in. So instead what we do in supervised machine learning is to provide examples of the kinds of things we're looking for. And there are different ways this might work in OCR, but probably the most intuitive one to understand is to think about this as training to learn to recognize images of individual characters. So what we mean by supervised learning is that we're going to provide lots of examples. We're going to provide lots of examples of images, so images of actual characters, how they look, and also outputs that we expect to be associated with those images. So we'd have one example, like this one at the top right here. We have this image of these black and white dots is our input, and our output is going to be this character number, this number 20,197, which to a computer represents the character E. And all we're going to do is to provide tens of thousands, hundreds of thousands of examples like this, and our learning algorithm, which could be using neural networks or something else, is going to try and learn the patterns between these input images and the outputs that we want to get. And to the extent that this model works well, it's then going to be able to make predictions on the basis of new images. So we're going to have given it lots and lots of images of each of our characters, but having built this model, it becomes possible for the model to make a prediction even on images that it's never seen before. So this is the kind of fundamentally important part to OCR, there's an almost infinite possible scope of different images that we might be accepting as input, and our model needs to be able to generalize from these specific examples that we've shown it before in advance in order to do well at this task. The last thing I want to highlight on this, again, is something which applies to supervised learning generally, is that our training data really needs to be consistent. We need to make sure that we're telling our machine learning algorithm, we're giving it examples that are labeled correctly. So if we're telling it that these patterns of dots are supposed to be recognized as this character E, we want to make sure that all of the dots we're giving it really are cases which should be recognized in this way. And so this training data becomes really, really important. And this is something which is applicable to machine learning or to supervised machine learning very generally, not just to OCR. But this is the kind of thing that we have to do generally to get from one kind of simple representation, so things like our mechanically captured images, to representations that have more semantic content. This is generally going to be something that's difficult, and it's generally going to be something that if we want a computer to do, we're going to have to apply machine learning of some kind to get it to do it. So I'm happy to talk more about OCR later if people are interested in that. But first of all, I want to come back to what I said earlier. So this transformative application of having these transcriptions and being able to do full text search, this is great, and it allows us to do text mining and so on. But there's some pretty obvious limitations to this. And I think the most obvious one here is that literal string matches, so matching these characters in sequence, this is still, it's a mechanical task. That's why it's convenient for computers to do. But because it's a mechanical task, it's ignoring all sorts of aspects of the meaning of text that as human beings we would think are really important. So there's no interpretation, no common sense, no use of context. And exactly the same things that apply to full text search on the basis of strings of characters also apply in the same way to simple text mining approaches. So this is probably easiest to demonstrate with a simple example. So a simple example would be something you might search for in a digitized copy of a Chinese text. So copy of a text like the Songshi, the history of the Song dynasty, and I want to search for all of the references to a particular historical person, a really famous one, Wang Anshi. This is a really easy case because there's only one person in the Songshi who's ever called Wang Anshi, and it's the guy I'm looking for. But in most typical modern digital libraries, there's nothing you can type into your search box that will give you exactly the results that I want. So you could type in Wang Anshi as your search string, and you'll find references in the text to exactly the sequence of characters Wang, An, Shi in sequence. It'll find all of those, but it won't find anywhere the same person is referenced just by his first name. So if you have an Anshi without a Wang, like in this second line here, which refers to the same person, this won't be found, this will be missed. And it won't find this third case, which actually refers to a different person, so I don't really want this one. So you might think, well, okay, I just modify my search string to just look for Anshi, and then I get the first two, but now I also get the third one, which I don't want. I don't want it because it refers to somebody completely else. It's some completely different person. It's the same sequence of characters, but it means something completely different. And when you get into it, there are plenty of examples that are much, much worse than this one. There are many cases where you have a sequence of characters that refers to a person's name, but it can also refer to something completely different that's not even a person at all. And so all these kinds of simple string matching approaches suffer from this problem. There's also other kind of related problems to do with the way Chinese is written, because unlike alphabetic languages, we don't have explicit delimitation between words. So if I search for something like ziyou on the left, I'm going to find cases where it refers to a person, but I'm also going to find cases where it actually refers to parts of two different words that just happen to be adjacent. And so for alphabetic languages like English, it's relatively easy to exclude this case. We could exclude it for Chinese if we added in word segmentation, so if we separated all of our words first. But that, again, is a task which involves adding semantic content. And even if we do that, this still doesn't solve the earlier problem of how to deal with context and the same exact sequence of characters as a word meaning something different in two different places. So this is something which brings us on to a newer, sort of more sophisticated representation of text that tries to layer additional semantic information on top of these transcriptions that we have. So semantic annotations are basically a really simple approach to get around this problem, or to try and start getting around this problem. And you can think of it like this. If these are our two sentences from our example before, where both of these have somebody referred to as Anshi, and it's a different person in each case. Ideally, what we do here is to layer on top of the text in a way that a computer can read information that essentially answers some really basic questions about what's going on in this particular line of text. So in our first line here, we have something which literally just means 48 in a sequence of 60. But in reality, that refers to a very specific historical date. It refers to a very precise date in history which we can identify. We then have this reference to Anshi, but it refers to a particular Anshi, it refers to a person, and it refers to a specific person. And it's not the same person as in the second case. So annotation essentially is just the process of saying, taking our plain text, which we could do some things useful with, and adding in the information that makes it possible to answer these kinds of questions. So layering on top of this information about the semantics of this particular letter or this particular sequence of letters at this particular point in this particular line of text. So if you're familiar with systems like ctext or Recogito or Marcus, you're probably familiar with how this often looks when it's presented. It often involves colored underlines or something like that, indicating that we have this information provided to a computer that says, well, this sequence of two characters here, which literally just means the first, actually refers to something much more precise. And this has to be recorded in some way that a computer can process. And this approach applies quite generally to many different kinds of things that we could annotate in a text. And there are different ways we could express this. Usually this is done using languages like XML, which allow us to kind of combine in a sort of somewhat easy to read representation for human beings, information that's machine readable to a computer that says, well, what does this thing represent? It represents a date. And which particular characters does it apply to? Well, it applies to these particular characters here. And we provide this other information in a way that a computer can process. So what I want to emphasize here is that this, again, is a new kind of representation that allows us to answer different kinds of questions, or to ask different questions of our text and have them answered very precisely by a computer that now, having been given this additional semantic information, being recorded explicitly, can now be answered in the same way by just performing mechanical tasks, just by going through and counting things in ways that don't introduce any error in the same way that things like machine learning and OCR do. So this is a visualization of the number of dates recorded, the number of precisely recorded dates by year across all of the 25 histories of traditional Chinese historiography. So at each year in time, how many precise dates were recorded in the Benji part of the historical record over time, and aggregating across all of the many different histories which cover the same period of time. This is a kind of question which you couldn't really answer just given a textual transcription of all of the histories. This would still be a really difficult thing to do. But once you have annotation that tells you precisely what these things mean, this becomes a trivial question for a computer to answer. So this is the same kind of difference between images and textual transcriptions. When we have annotated transcriptions, again, different kinds of questions become easy to answer procedurally just by asking a computer to go through and count things in a particular way. So how do we get these things? Again, the same kind of thing applies as to textual transcriptions. The easiest way we can get textual transcriptions isn't to do OCR. The easiest way is to go and find some people and ask them to type in all the characters. We can do these things manually, and we can do the same kind of thing for creating annotations. We can create them manually, or we can create them with some minimal assistance from a computer. So if you think of a text here with these grayed parts as being potential annotations we might want to add, if we have this reference to An Chong Rong, these 3 characters here, if our system knows that there's a person with that name, it's very easy for it to suggest that this location of the text here might refer to that person. It might do, it might not, but this is a candidate which we may or may not want to add here. So computers can help us with manual annotation. But what's more interesting is the way computers can help us do annotation semi-automatically and automatically based on data. So this is another example here where we have our text, supposing we want to add annotations to it, and all of these grayed out annotations are suggestions that a computer's proposed. here we have a reference to somebody called Wang Xian, and this is an example of why annotation is generally going to be a difficult task. It's generally going to be a difficult task because there are going to be lots of different candidates. Each row in this yellow table here corresponds to a different historical individual called Wang Xian, who is sufficiently well known that we have information in scholarly databases about that individual. And so you can see here we've already got, I think, eight different people who this could potentially be. The reason for choosing this example is that in this example, these databases tell us enough information about these individuals that together with the text, just the text that we have here on the screen, it's possible to be certain which one of these it is, and it's also possible for a computer to reason and say which of these is the most likely candidate here. And the reason that one of these jumps out as being the most likely candidate is that this combination of this historical office, the Shumishi, and the reference to Wang Xian is special in that one of these Wang Xians happened to previously have held this particular office. It's had this title, and therefore this pair of candidate references here is almost certainly going to refer to that specific Wang Xian as opposed to any of the many other candidates that we have. And so this is where there's this kind of connection between annotation and data. It's possible to annotate things to say which things are, say, referring to some kind of person without a lot of information about the individual people. But if you want to disambiguate and say that this reference is to some specific individual, you need to have information about those individuals. And if that information is machine readable, then computers can potentially do a lot of work in helping you create these annotations. There are lots of cases of basically the same thing. If you think about this case where we have a reference to Sichuan Zongdu Guilin, Guilin in Chinese is going to be ambiguous on its own. It could refer to a place or it could refer to a person. But if we already have the information that this particular person whose name is Guilin held this particular office, then we can again immediately infer that this particular case here, this particular instance, is going to be a person. Not only is it going to be a person, but it's going to be this specific person. So this kind of information makes annotation much easier. And there are lots of other cases that are very, very similar. So part-whole relationships of place names. Place names historically are going to sometimes be ambiguous. So a reference on its own to Ninghua could refer to this place, or it could refer to this place. But in this particular context, because we have this reference to Dingzhou before it, it's definitely going to refer to this one. And we can infer that automatically if we have the information, either in a human-readable way, in which case a human annotator is going to have to look at this and decide, or if our data is in a machine-readable format, a computer can decide this for us. And obviously, that latter thing is what we want, because computers making these annotations for us is going to save us a ton of time. This is a very similar example here, where we have era names are also going to be ambiguous. Things like Yongjia, there's more than one era, which is called Yongjia. But if we have information about, in our text, about which ruler is associated with it, that's going to make it very easy for us to process this automatically and get the correct results. And again, a bit like OCR, there's some things where we have kind of easy cases where we can use rule-based approaches that we don't need anything as fancy as machine learning for. So things like unambiguous references to eras. If we have an era like Chenghua where there's only one of them, and after that we have some reference that's unambiguously to a particular year, a particular month, a particular day, then we can just automatically annotate this kind of thing very, very easily. But the more general case is going to be much harder. The more general case of creating annotations is much more similar to the more general case of OCR, where what we really need to have is some kind of machine learning approach that makes use of existing data. So again, we're going to need to have label data that says, given as input some sequence of characters, so our input on the right here, you can think of this as being a sequence of characters that have no annotations. We can turn this into a supervised task by recording, based on annotations we already have, what we think the correct annotation is for this. So for example, here we would say this Wunian is going to be a date, this comma is not going to be annotated, this part here is going to be an office, this part here is going to be a person, and so on. So if we have annotated data, we can turn this into a supervised task and apply machine learning to it, and this process is called named entity recognition if we're just looking to identify which things are particular types, so which sequences of characters refer to people versus offices. But also, we're also going to need to do something called named entity disambiguation if we want to do the more interesting task of saying, okay, so this reference here to these three letters corresponds to a person, that's relatively easy to identify. If we want to also say this corresponds to this particular person who also occurs in other places and who we know certain things about, that's actually a considerably more challenging task. Okay. Forgetting the details of how we actually do that task for the moment, one general observation, as we said, data makes annotation much easier. In fact, without data about the things we want to annotate, it's almost impossible to annotate them in any reasonable, principled way, because we have to know, if we want to disambiguate this person as being the same as this one or this other one, we have to know something about the differences between those two people in order to do that. A related observation is that having these annotated representations, okay, this is useful if we want to do text mining or data mining or say things about our text, but it's also something which makes it really easy to extract certain types of information from our text. And this is important because these pieces of information we can extract then feed back and allow us to do annotation more effectively because we know more information about the entities. And if you read Chinese, this is an example which hopefully makes that kind of more intuitive. If you suppose we want to extract information from this line of text that tells us something about the connection between a person, a particular bureaucratic title, and a date, this is, if I just give you this piece of information, that's almost impossible to do. It's extremely difficult. It's almost impossible because it relies a lot on context, because this reference to a date is implied contextually. It doesn't give you all the information you need to interpret which year and month and day that is. But for a computer, there are also bigger problems of which parts of this sentence, of this sequence of characters, which parts refer to what kind of things, which things refer to names of people, which things refer to names of offices, and so on. And that's challenging for a computer as well, because there are also superficially different cases where you have superficially exactly the same structure, but meaning something very different. So this pair of sentences here, the first one was on a particular date, some particular person held some particular office title, whereas the second one is on some particular date, a date was taken as being the date for some named event. So this named event was stated as being the 10th of April, say. And the key thing here is when we have annotations, these things become trivial to process because we have patterns of annotations that we can infer things from. So we can infer things from saying, if we have on a particular date, a person held an office, we can treat that entirely differently to the second case, where there are no people involved and no offices involved. And so this means that if we have annotated representations of text, there are lots of cases where we can mechanically infer, just using a simple computer program, using very, very simple patterns, useful pieces of information about historical entities just on the basis of that text. And this would be very challenging without the annotations, but with the annotations, this is almost trivial to do. So if you have some piece of text that's annotated and says, at some particular time, whatever time that was, whatever date, some particular person, doesn't matter who, became some particular bureaucratic title, you can infer from that a machine-readable claim that connects these things together. And you don't have to worry about this going wrong because of uncertainty or ambiguity, because your annotation already made it precise exactly what each of these things referred to. And there are many, many, many other cases of this, so things like dates of birth and dates of death, people who killed other people, people who were the father or the son of other people. Once this information about the entities is recorded precisely with their reference, it becomes possible to extract these relationships very, very straightforwardly. Annotation's hard. Annotation's hard because a lot of the time the people involved are not these famous people like Wang Anshi, who don't have other people who happen to share their name. Very often we're going to have cases like this, where you have somebody called Wang Zuo, and this is a screenshot from Chinese Wikipedia of all of the historical people who are famous enough to have a Chinese Wikipedia article about them, who all have exactly the same name. So the annotation task requires having enough information about these entities to decide which one of these it is, and also to decide whether a particular reference isn't to one of these individuals at all, and is to somebody who we don't have any information about. This is connected with this idea that a lot of the knowledge we have about the past, particularly about famous people, or people who are sufficiently famous to be attested to in these historiographic sources, a lot of the information we have about these comes directly from these historiographic sources. And this is just a randomly chosen example by going to Chinese Wikipedia and looking at the citations here. you can see the citations for information about this historical individual, even in a modern encyclopedia, the vast majority of these come from sources like the history of the Song dynasty or the Shu Cizhi Tongjian or these other historical sources. So these are important sources of some information about these historical individuals. One other kind of representation that I want to talk about finally is how we represent information about historical entities generally. And again, there's this kind of connection going back to pre-digital sources. One kind of pre-digital reference source you might have is this kind of index to historical individuals in a particular dynasty. So this is from this index of biographical information about people in the Song dynasty here. You have this kind of textual information, and very much like an index or a concordance, it has headwords. In this case, the headwords refer to people, and then you have information recorded about them, so their approximate dates of birth and death, where they're associated with, other information. And obviously, in the modern era, this kind of information is usually represented in things like databases. This is an example here from the China Biographical Database Project, or CBDB, that corresponds to the same kind of information about the same person referenced on the left here. And the most important thing about this for us, if we're interested in doing text and data mining or any kind of computational processing, is that the data on the right is now structured. Structured data because it's recorded mostly in different database fields. For example, we have a year of birth field, and this is going to record the same information for thousands of different people, or hundreds of thousands of different people, but each time we're going to record their year of birth in the same place, if you like, in the same kind of location where a computer can compare these across all of these hundreds of thousands of records without any kind of difficulty. And this works, or this is useful, or easy to process, to the extent to which it's consistently recorded according to some known formalization. So in other words, there's some particular principle that we've used to organize our data, and we've been consistent in how we've done that. And if we've done that consistently, then this data becomes very, very easy to process using Python or whatever other kind of computational approach we want. And obviously, this makes data mining of this kind of structured data relatively easy. This is an example not created by me. This is created by the CBDB team themselves of the age in years at time of death of female persons recorded in their database. And you can see there are some interesting features here. For example, they're a dual peak in terms of the kind of typical dates of, typical years of age of death of these individuals across the data. And this is the kind of thing which you can do trivially when you have a database that records this information in these database fields. So this is great, but this is something I want to use to motivate this issue of connecting data across databases. So when we have data recorded in any database, to the extent that it's well recorded and consistent, we can do this kind of text and data, this kind of data mining on these materials very easily. If you're familiar with databases, probably familiar with this kind of picture. Databases, relational databases typically work like this. You have tables of data, and each table represents information about some particular kind of thing. So this is a real example from CBDB, where this is a table of people, and so each row represents information about one particular person, and each column, these are the fields we're talking about, each column records one particular type of data. So this could be the year of birth, and so obviously the intersection here corresponds to the year of birth of this particular person whose information is in this column, in this row. Databases are based, or relational databases are based on this really simple idea. The first extension to this that you'll see if you learn about relational databases is that very often it's going to make sense for us to store data in another table. And when we do that, we're going to use identifiers to connect information between these tables. So supposing we want to record information about our person Wang Anshi, we want to record the information that he's associated with a particular dynasty. So we could write in here, we could just write Song dynasty. If you're familiar with databases, you probably know that there are good reasons why we won't do that. And the reasons we won't do that are typically going to be that we really want to record additional information about that other kind of entity. We want to record information about the Song dynasty as well. And we don't want to have to record it and repeat it in every row for every person who has something to do with the Song dynasty. And so in order to avoid doing that, what we'll do is to create a new table that records information about dynasties, like this table here, and it'll have a row in it that corresponds to the Song dynasty, and it'll tell us, say, which years the Song dynasty corresponds to. And then in order to link these two tables, we'll use an identifier. And this identifier here is the number 15. So all that means is if we want to say that somebody in our person table is from the Song dynasty, we're going to write down a 15 in this column. So there's nothing particularly fancy or unusual about that. But this idea of linking things using these identifiers is something that I'm going to refer to as an idea of using an internal identifier. So there's no particular reason why this has to be 15. You can see looking at this table, the only reason it's 15 is that the way these dynasties were written down in this particular database, this happened to be the 15th one that was entered. Could have been 16, could have been 12, could have been a different number. And this is one example of something that's much, much more general when it comes to recording things in databases. And this is something that's really easy to see. If you pick two databases that cover humanities data on things which have the same kind of entities or similar or overlapping entities, so for example, databases that include biographical information about historical Chinese people, that's the example I'm using here. If you compare any two of these and look closely at the data, you'll find that there are huge numbers of differences in how the data is conceptualized. And this doesn't just refer to things like choosing a number 15 versus 16 versus 17 for these internal identifiers. It includes all sorts of much more fundamental things, like how we record information about dates, or about places, or about dynasties. So in the case of the Song dynasty here, are we going to distinguish between the Song dynasty, the Northern Song, and the Southern Song? Are we going to treat these as three separate things? Are we going to join them together in some way? Even just thinking about something as simple as the names of a person, how are we going to conceptualize that? If we look at this example from another important biographical database here, Academia Sinica's one, the way they've conceptualized names is by saying, well, we start out with a kind of main name for a person, and then we have the alternative names for a person. And the alternative names are categorized according to various possibilities. It could be their style name or their art name, or it could be their name in Hanyu Pinyin, in Roman characters. And you might think, well, it doesn't really matter which way you do this, and that's right, in a sense. It doesn't really matter which way you do this, as long as you're consistent within your database. The problem comes later on if you want to actually connect information across these databases and ask queries of the combined information. And you can see this is really problematic for dates as well. That's on the next slide here. This is, again, a comparison between CBDB on the left and in this case, Dharma Drum's personal authority database on the right. There are endless different ways you could record this information. In CBDB, this has been done in two ways. We have a reference to the Chinese era, and then we have a year, an approximation in Gregorian or Julian calendars for birth and death years. In this other system, we have instead a very precisely recorded range of dates for each. So date of birth is given as a range representing uncertainty in Julian or Gregorian calendar dates, and the same for year of death. So even for representing something as simple as the year of birth, or the date of birth, rather, of a person, there are a huge variety of different ways we could represent this information. And that's in addition to technical representations of information. Some systems are going to use tables of relational databases, like CBDB on the left, and some systems are going to represent this in completely different ways. So for example, using XML, using this hierarchical representation based on annotation here on the right-hand side. And does this matter? So depending on what you want to do, this might not matter. In one sense, this doesn't matter. If all you want to do with these materials is to work with them in the same way as you might with printed reference materials in the library, this doesn't really matter, because if I have two printed reference materials and I want to look up Wang Anshi in both of them, I just look at their index and I find the page in each of them, and I compare them side by side. And that's great, and I can do that. And you can do exactly the same thing with digital systems, and none of the issues that I mentioned earlier really matter all that much if that's what you're trying to do. But as soon as you want to try and combine the data from them and to do any kind of analysis computationally, this really matters. This matters because every time you want to join information across these systems that use very different conceptual schemes and also technical implementations, you're essentially going to have to write some code to say, how do we join these things together? And of course, it's not that you can't do that, it's that this adds this extra obstacle that makes it harder to deal with these representations than if we didn't have to do this, than if we could have our computer merge these directly for us. And so this finally is where I want to get onto this idea of linked open data, the semantic web, and the resource description framework. And this is, if you like, the recommended approach by the people who design the World Wide Web to getting around this kind of problem going forward. So to how we can actually design and implement systems that allow us to meaningfully connect these projects without saying we're going to have to standardize and everyone's going to have to agree on saying we record everything in exactly the same format, which isn't really a feasible thing for people to do. This is based on two kind of core ideas. One of these, which I think is really interesting and neat idea, is that we're going to represent everything using one consistent format. Everything we want to talk about, we're going to represent using a URI. And a URI is basically something that looks identical to URLs. It looks like the kind of thing you type into a web browser, but we're using it differently. We're using this to represent concepts. So whenever we write down this concept, so say this one on the right here in blue, whenever we write down this sequence of characters, what we're going to mean by that is the same thing. And I'm going to use that to represent this historical individual, Wu Sanquei, for instance. The reason that this is a useful or interesting thing to do, it might seem like a really weird thing to do initially, is if you think back to that number 15 that was representing the Song dynasty in CBDB, I think it's safe to say there are going to be millions of databases in which the number 15 represents something. In that particular database that I chose, in that particular table, the number 15 represents the Song dynasty, but only with those important qualifications. If we'd added information at the start that said HTTP CBDB and then added information dynasty and then 15, this would then become a completely globally unique identifier that always refers unambiguously to that same idea. And that's all that's going on with this identifier idea in RDF. We make everything very precise so that every time I use this identifier, you can think of this thing, you shouldn't really think of this thing as being a URL that you type into your web browser. You should think of this as being analogous to the number 15. It's just an identifier that's now longer, but by making it longer, we've made it unambiguous and made it possible to refer to that in completely different systems in a way that has no possibility of misinterpretation by a digital system processing it. So that's kind of, I think that's the more interesting thing about RDF. The second important caveat about it is that data's only ever recorded in a really simple form. It's only recorded in the form of triples, where we have statements of subject, verb, and object. And that's it. So we don't have a lot of complexity of structure. Instead, we build up this complexity of structure by making lots of really simple statements. And this is one way of saying that this is a graphical model of data. So it's the kind of model of data that I'll show you in a second we can represent using a network graph. And these things that we're going to talk about, these are going to include not just people, places, offices, and so on, but these are also going to include the concepts that we want to talk about. So the concept of a person having a style name, or the concept of a person having held a bureaucratic office, these are also going to be things that we're going to assign universally unique identifiers to so that they can be used in many different contexts. So I think I already said this. Why would we use URIs? The key idea here is that different groups can assign their identifiers without risk of overlap. Because if I assign the identifiers for ctext and nobody else assigns the identifiers for ctext, we're never going to overlap. If Harvard and CBDB put Harvard CBDB at the start of their identifiers, and these identifiers, these domain names, we already have a system for allocating these to individuals and organizations uniquely, then these identifiers can never overlap. So it seems like a trivial point, but when you move to a web scale, it's no longer a trivial point at all. A big upshot of this is that it gives us a common way of representing data and also a common way of querying data. And this can be expanded to include things like federated querying, where you ask a question of one system, and in order to answer that question, that system goes and asks other systems, which also support the same kind of data structures. This is a graphical approach. This is what I mean by that. If you were at the workshop last week, you'll be familiar with this kind of picture. The idea is that each of the things we're going to talk about, all of our entities, are going to have connections to one another. But these connections are only ever going to be expressed through direct edges, because everything is going to be a subject, a verb, and an object. We have no more complex representations of data than that. I'm going to skip over that example. One of the beneficial consequences, as I said, is we have this standard query language, so it's possible to ask questions of, say, CBDB's data using exactly the same language that you can ask questions of ctext data. And in the future, it's possible, well, it's already possible if you load these into your own system, to ask questions of both of these joined together. And part of that comes back to this idea of saying, we're going to make all of our identifiers completely unambiguous. So there are going to be plenty of things in CTExt that internally we're going to use the number 15 to refer to. But if we're using semantic web and RDF, there's no issue here because all of our identifiers are unambiguous. So nothing is going to be just a 15 on its own. There's going to be no collision between these different systems. Okay, so I'm almost done. The last thing I wanted to say a couple of things about was large language models and language modeling in general, because of course that's been in the news over the last few months with things like ChatGPT. These have really made a huge amount of progress in machine learning and deep learning for processing natural language, and this is very relevant to some of the representations and things that we're talking about here. Obviously, you can think of one of the most basic things that language models are trained to do as being predicting the next word in sentences. So given these tokens, predict the next one. This seems like a kind of trivial thing to do, but in reality, what we found over the last decade or so is that training machine learning models and deep learning models to learn how to do this really well allows them to internalize a lot of what we think of as being common sense language ability in a particular language. In other words, this is a kind of pre-training of general models that we can apply to do very well at downstream natural language processing tasks. And one of the reasons this works really well is that unstructured and unannotated text is really cheap. So I've been talking about all of these more sophisticated representations of text where we have all of this semantic stuff layered on top. Those are expensive to produce because annotation's hard. Unstructured text is really cheap to produce. And even for pre-modern Chinese, there's a lot of this stuff around. I'm going to come back, so this is coming back kind of full circle to one thing that I tried to emphasize before. This is just one really simple application of that, so automatic punctuation. If you're at the CTExt workshop, one of the things you'll have seen me showing was these connections between our image sequences and these transcriptions, and very often we're going to have punctuation layered on top of these. And if you look closely, or if you think about it for more than a second, you're going to realize there's stuff on the right that isn't there on the left. There's punctuation in these texts that's been added on top. And this punctuation, similar to the kinds of semantic annotation we've been talking about, these are actually adding semantic information on top of this text because you have to understand what the characters mean and what the words mean in this particular context in order to put these punctuation marks in the correct place. It's not something which is simply decided by the sequence of characters here. You also need to have some competence of the language to know where to put these things. And this is the kind of thing that deep learning does pretty well at. And one of the reasons it does really well at this is because we have so much training data. Because all you need to do to turn this into a supervised task is to take out the punctuation from the examples you already have of punctuated text. And so this is a real example here where I've highlighted the errors or the discrepancies between the output we got for deep learning from an unpunctuated text. So asking a computer to go and insert the punctuation in this text on the left versus, if you like, the gold standard for how this text was previously punctuated on the right. And the reason for choosing this example is to highlight, if you like, the inconsistency. One of the problems we have here is, if you look carefully, there are many cases here where you could argue that either of these is correct. It's not simply the case that all of these punctuation marks that are different in the model are fundamentally incorrect. And if we actually look at our training data, we'll find that there are other cases that are directly analogous, where our training data, in fact, is inconsistent. In other words, people punctuating text have actually punctuated it inconsistently in the training data that we're using. And so this is coming back to this idea of when we do OCR, we don't want to have any mislabeled characters. When it comes to doing semantic annotation, whether it's something as simple as adding in punctuation, or whether it's something more complex like annotating these named entities and so on, one thing we're going to have to be really, really careful about is making our training data as consistent as is possible. Because if our training data is inconsistent, we're essentially asking our computers to try and learn to solve an impossible task rather than just a very difficult one. Okay, so that's pretty much all I'm planning to say. Summary, better semantically enriched representations are useful for various purposes. Hopefully I've persuaded you of that. But they're difficult to get, and they're difficult to get for the same reason that OCR is difficult. They rely on something approximating understanding or mimicking understanding, like in machine learning or deep learning, to create them. But we're getting increasingly good at performing these approximations and doing them well. And supervised machine learning still has a lot of applications to pre-modern text. One of the things we need to be careful with here is making sure that our examples, however we collect them, can be as consistent as possible. But thanks everyone for listening. I will stop there.